Hello dear students, today is the second class of complex number. This is the second continuation class of your previous class. So today in the previous class we discuss about polar representation of a complex number. Today also we discuss about some geometrical interpretation and very important concepts of some complex numbers, mainly focusing on geometric view of the results. So let us have two complex numbers, z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. So these two complex number, non-zero complex number. Let us first draw the Argand plane or the Gaussian plane or the complex plane. So this is your Argand plane or Gaussian plane, or we can say a complex plane. This is origin, this is real axis, and this is your imaginary axis. Now suppose this is your z. I want to show first where is the position of z bar and where is your negative of z. So this is the position of z complex number, any complex number x comma y or x plus iy. So this is the position of z, as you can see. So z bar is the mirror image of z reflected across the real axis. So what is your z bar? Mirror image of z. So this is your z bar, this is your z bar, mirror image of z reflected across the real axis. Okay, this is your real axis, so this is the position of z bar. And where is your minus z? Minus z is, this is your minus z, negative of z. So this is reflected through the origin. Okay, so you see z minus z and z bar are not collinear, these 3 points are not collinear. So this is the position. And where is your mod z? Mod z is this one, that is the distance of z from the origin, positive square root over imaginary real part square and the imaginary part square. So this is your modulus of z. So now we will describe the addition of two complex number. So in the same diagram, let us draw another complex plane. Okay, so this is your complex plane, this is your real axis, this is again your imaginary axis. Now we will show the addition and subtraction geometrically. So suppose this is your z1, this is your, sorry, so this is your z1 suppose, and this is another complex number z2. Let us complete the parallelogram with z1 z2 as the sides. As you can see the parallelogram, so their diagonal look at the diagonal, it's not straight. Yeah, so this is the diagonal. This diagonal is represented by just like a vector z1 plus z2. So z1 plus z2 is the diagonal of the parallelogram with z1 comma z2 as tips of adjacent sides. So this is also z1, this is also z1, this is z2, just like a vector, and this is z2, this is origin. So this side is minus z1 z2, sorry, this side is minus z2, and again this side is also minus z2. So let us complete the parallelogram. The diagonal of this parallelogram this is Z1 and this is minus Z2. So diagonal of this parallelogram represent the difference between two complex number, that is Z1 minus Z2. So this is how geometrically we represent the complex number addition of two complex numbers Z1 and Z2, these two complex numbers, and their difference Z1 minus Z2. So this is how we represent the addition and subtraction of two complex number. So let us now see the actual diagram. This is the diagram, and also the representation of Z bar, modulus, conjugate, modulus, and the negative of the complex number. So next we will state a very important theorem. If Z1 Z2 be non-zero complex number, and argument of Z1 into Z2, that is their product of two complex numbers is given by argument of Z1 plus argument of Z2 plus 2k pi, where k is an integer such that k is 0 if minus pi to pi, argument of Z1 plus Z2 lies between minus pi to pi, and 1 if it is lies between minus 2 pi and minus pi, and it will be minus 1 if it is between pi and 2 pi. So this is the range. Let us see the small proof of this. Let Z1 can be represented by R1 into e to the power I theta 1, as you know from the Eulerian expression. Just like e to the power I theta is from the Euler, we know that e to the power I theta is nothing but your cos theta plus I sin theta. From there we can write that Z1 is this and Z2 is R2 e to the power I theta 2. So the product is given by R1 R2 into e to the power I theta 1 theta 2, provided that theta is the principal argument, theta 2 is the principal argument. So what is your argument of Z1 Z2? That is theta 1 theta 2 plus 2k pi, where k is an integer such that theta 1 plus theta 2 plus 2k pi lies between minus pi and pi, excluding minus pi. Okay, but we know that if theta 1 is between minus and pi and theta 2 is between minus pi and pi, their sum will be between this. So when k is equal to 0, this value lies between this. Okay, and when k is equal to minus 1, this value pi less than theta 1 plus theta 2 less than equal to 2 pi, then in that case this range lies between minus pi and 0. So we have k is equal to minus 1. Similarly, we can explain that k is equal to 1, okay, from this result, because we want the principal value of the argument. So that gives you the idea that this argument of Z1 and Z2 is not equal to argument of Z1 plus Z2, provided that this argument of Z2 lies between minus pi and pi, in that case k equal to 0. So argument of Z1 Z2 not equal to always argument of Z1 plus Z2. Be careful when you are applying this product. Similar explanation can be made for the division also. Look at that, similar explanation also can be made. Now let us have some geometrical interpretation of the product of two complex number, because without this idea of argument of Z1 Z2 we cannot give you the idea of the product of two complex numbers. So again I am writing Z1 is equal to R1 e theta 1 and R2 e to the power I theta 2. So their product is given by this. So modulus is R1 plus R2 and argument of Z1 Z2 is theta 1 plus theta 2. So now we have to draw something on the argand plane. Let us draw OE. OE is equal to 1 unit and complete the triangle. OP1 represent the complex number Z1 and OP2 represent the complex number Z2. Look at that. So OP1 is R1, OP2 is R2. This angle is theta 1 and this angle is theta 2. So we complete the triangle OP1 UE, okay, and taking OP2 as base we complete this triangle OPP2. Look at that triangle, this triangle, I am talking about this triangle, and this triangle already drawn, completing OP1 E1. Now these two triangles are similar triangles. So using the similarity property, OP by OP1 equal to OP2 by OE, as OE is 1, we get OP is equal to R1 or R2. Since OP1 is equal to R1 and OP2 is equal to R2. So also we have, so this OP represents R1 R2. Okay, clear? This OP represents R1 R2 by using the similarity properties of these two triangles, and from the information that OP1 and OP2 is given to you. Also angle P2OP, P2OP, that means this angle is equal to EOP1, similarity. So this angle is nothing but your theta 1. So this total is your theta 1 plus theta 2. Look at that from the diagram. This angle is your theta 1 plus theta 2. This angle is your theta 1 plus theta 2. Okay, clear? So this is the representation of product of two complex number. That means P represents the product of two complex number R1 R2. Hence P is the complex number for which the modulus is R1 R2. Okay, and the argument is theta 1 plus theta 2. So in this way we can represent the product of two complex numbers. Clear? Similarly, we can explain the difference division. We can division of two complex number. Okay, by drawing a same type of diagram and using similarity. That is, I want to try this one. So I am giving students to try for this by drawing help of this diagram, this method. You just try for this. Okay, R1 by R2 by taking division. So let us now explain some interpretation, very important interpretation in complex number theory. So if Z1, Z2, Z3 are three complex number vertices of a triangle ABC, okay, described in the counterclockwise sense. So let us draw the complex plane or argon plane, OX, real axis, OY, imaginary axis, this is O, and this is the triangle. Okay, this is the triangle. So this is your A, this is your B, and this is your C. A represents the complex number Z1, B represents the complex number Z2, and C represents the complex number Z3. Clear? So what does represent argument of Z3 minus Z1 by Z2 minus Z1? This represents the angle between AB and AC. This represents the angle alpha, angle BAC. Okay, because look at that, Z1 is A, B is Z2, and C is Z3. So this represents the argument of this Z ratio represents the angle alpha, and simply the ratio represents the, actually Z2 minus Z1 represents the line AB and Z3 minus Z1 represents the line CA. So this represents the complex number, this ratio represents the complex number CA, this length CA by BA, that is modulus, and their included angle cos alpha plus I sin alpha. Okay, similarly we can explain this can be explained from this result. You look at that result, Z1 by Z2, so this can be explained. Okay, now there is an important note. If Z1, Z2, Z3 is collinear, that is alpha is equal to 0 or pi, then look at that, this relation become argument becomes 0. So this will give you Z3 minus Z1 is, Z2 minus Z1 is purely real. This ratio becomes real because alpha is 0. Okay, alpha is 0, sin alpha 0, cos 0 1. So this will be purely a real number, or pi, in that case also we will get a purely a real number. So this is important to note. Okay, now we interpret argument of Z1 minus Z2, Z3 minus Z4. So again we have the argument, again we will draw a argon plane. So two lines joining Z1 Z2, this is joining Z1 Z2, and this joining Z3 Z4. Okay, so what does it represent? Argument of Z1 by Z1 minus Z2 by Z3 minus Z4 is represents the angle between these two lines, that is, it represents the angle alpha. The line joining Z4 Z3 is inclined to the line joining Z1 and Z2 at the following angle. So this represents the angle between this. So I hope these two representations are clear to you. Now let us explain more some important geometrical results and equation. Distance formula. What is the meaning of that distance formula? Suppose AB represents two complex number, already you have an idea about that. Suppose this is Z1, this is Z2. So distance formula is nothing but your AB is given by Z2 minus modulus of Z2 minus Z1. Just like in straight line we have the distance formula root over x square, this is also give you the modulus value. Okay, section formula is same. Suppose there is a point P, then and these two ratios as m is to n, so same as the Cartesian coordinate system, we have the same section formula result. Okay, the same formula will apply. So from there we can say that midpoint, we can say if m is to n is 1 is to 1, that is, then we can say the midpoint formula the same as the Cartesian. Now how will you define the parallelogram? Condition for parallelogram: the diagonal AC and BD bisect each other. You know that if you draw the parallelogram like this, then if this is the parallelogram and A, B, C, D represents the complex number Z1 in counterclockwise sense and represents the complex number Z1, Z2, Z3, Z4, then the diagonal AC and BD, this is the diagonal AC and BD bisect each other. That means in this case we will get the condition Z1 plus Z3, Z1 plus Z3 equal to Z2 plus Z4. We will get Z1 plus Z3 is equal to Z2 plus Z4. Okay. So this is the condition for parallelogram. Rhombus, whatever diagonals bisect each other. So draw the rhombus first. This is the rhombus. So again we are drawing A, B, C, D. Okay. So this is the diagonal ACBD. Now the diagonals ACBD bisect each other. In that case also you are getting this result. Okay, and the pair of two adjacent sides are equal, that is AD equal to AB. Pair of two adjacent sides are equal. This is the additional condition for rhombus. Okay, in that case we will write modulus of, that is the distance formula, modulus of Z4 minus Z1 equal to Z2 minus Z1. Clear? So this is how you can explain the conditions for rhombus. Square you can easily find out, because AB is valid for this, AB conditions are valid for square, and there is additional diagonal additional result, AC and BD are equal. Rectangle A and B, it follows from A and B, that is these two results are followed for rectangle. So if you draw the rectangle, this is your rectangle, you can easily explain from the previous one. So this is how you represent the plane geometry. Now we will define equation of a straight line. So equation of a straight line, suppose Z be any point on the line joining Z1 and Z2. Okay. So this is your line, this is your A and this is your B. So A is your Z1 and B is your Z2, and Z is any point on the line, then we can say argument of Z minus Z1 by Z minus Z2 is equal to 0 or pi. From the previous representation, already in the first introduction of this class, we explained this term. So 0 or pi, that gives you Z1, this ratio is a real number, already explained in the previous section. So this gives you modulus of Z minus Z1 by Z1 minus Z2 is equal to the conjugate of this. This gives you the real part. If this is real, Z is equal to Z bar gives you the real part. Z is equal to Z bar will give you the real solution. So this gives you nothing but the, we know that from conjugate that Z conjugate can be separated and splitted into two parts, that is Z1 bar Z minus Z1 bar, Z1 bar minus Z2 bar. So simplifying, this will give you the straight line. This will give you the equation of the straight line. Look at that, it's very simple, nothing to remember. Just remember that you take a line Z1, Z2 and any point Z and write this ratio, argument of this, and this is a real number, and then some manipulation will get this equation. Now what is the general equation of a straight line? So I will give you the idea. We know that in Cartesian Ax plus by plus c is the general equation of a straight line. So here z is equal to x plus iy. So z bar is the conjugate x minus iy. So x is given by z plus z bar by 2 and y is given by z minus z bar by 2i. So substituting x and y, and after so substituting x and y here in this equation 1, and after some manipulation we will have this result. This is the equation of a complex equation of a straight line. This is the equation, or we can say general equation of a straight line in complex number. So alpha is a plus ib. Alpha is a complex number and k is a real number. So alpha bar z, look at that, plus alpha z bar plus k equal to 0. This gives you the complex form of a straight line. What is the complex slope? Complex slope is given by mu is equal to z1 minus z2 by z1 bar minus z2 bar. Look at that. This is from this equation. This is from this equation. This gives you the complex slope of a AB. This is also you have to remember, that is from calculated from here. You can easily calculate from here. The slope of this line is this, and also slope of the line this, that is already the general form. What is the slope? Minus of alpha by alpha bar. Okay. Now we'll explain equation of a circle. Let us draw a circle. If the center of the circle is z0 and the radius is r, so its complex equation of the circle is given by modulus of z minus z1 is equal to r. That is the distance, that is z is any point on the line, on the curve of the circle. Z is anywhere on the circle, circumference of the circle. So this distance is always r. So that is why the equation is z mod of z minus z1 equal to r, z minus z0, because z0 is the center and r is the radius. So this is the equation of the circle. So we can write mod z of z square is equal to r square. So that will give you, as you know, mod z square is equal to z into z bar is equal to mod z square. From this result we can say this is the equation of the circle, more expressed in a more compact form, and after some manipulation, that is taking alpha is equal to minus z0 and k is equal to z0 bar minus r square, we have this expression. This is the general equation of a circle, either this or this. This is the more compact form and this is the general form. And where is center is minus alpha, and alpha is given by minus z0 and radius is this, that is root over alpha bar minus k. So this gives you the equation of the circle. Okay. So this is very very important, equation of a circle. So by observing this result you can say this is the equation of the circle. So I hope today's class is very helpful to you. I gave you the geometrical idea of straight line, circle, and some geometrical interpretation of some important results in complex number. So look at the next video, that is the third class on complex number, and subscribe my channel. I hope that video will be also helpful to you. Thank you.